All right, in this video, I'm going to go over the solution to the easiest lysimeter problem ever, because there are virtually no unit conversions you have to do. Everything's in the metric system, and pretty much it's all laid out really simply for you. So let's explain what's going on. So on the left here is the lysimeter, and it is full of a mixture of soil and moisture, and there's vegetation in there too. So there it is, full of soil and stuff, and it's got some kind of vegetation on the top, looks like maybe grass or something like that. And the area of the surface is 2 square meters, 2.00 square meters. And the way this lysimeter works, it's a weighing lysimeter. So we're going to restrict the inputs and outputs to the following. So input is going to be precipitation in, P. There is going to be drainage out that we're going to capture and measure. And we're going to then very carefully weigh the lysimeter or the lysimeter monolith at the beginning and end of our experiment to see how it's changed, and we will use that to determine the change in storage for the lysimeter. So if we write the storage equation down, it's going to look like this. It's very simple. We have the change in storage equals inputs precipitation minus outputs, which are ET. That's the thing we're going to ultimately try to measure, minus drainage. And we're going to measure P, we're going to measure D, the drainage. We're going to measure the change in storage through the mass in kilograms. That's the only way in which this problem is different than the water balance problems you solved earlier in the class. We're going to weigh the measure. We're going to determine the change in mass and convert that to a change in volume of water stored. So we're going to know this, we're going to know that, we're going to know this, and then we're simply going to rearrange this to solve for the ET, which is going to equal delta S, the storage, minus P minus, did I do this right? Let me correct this. ET is going to be P minus D minus the change in storage. There we go. And that's the equation we're going to use. Now, to make this problem super easy, we're also saying that right next to our lysimeter in the ground, we're going to place a straight huge rain gauge with a surface area of exactly the same as our lysimeter of 2 square meters. We're going to capture the rain that falls during this period of 1 day, and that's going to be a direct measure of the precipitation in volume per time. So after 1 day, so we're going to go, it's going to be a 1 day experiment. And after 1 day, we're going to capture in our rain gauge, we're going to capture 0.0076 cubic meters of precipitation, of rain, of water. So that's going to be our precipitation in 0.0076 cubic meters per day. We don't have to convert anything because we're actually capturing it in a rain gauge right next to the lysimeter. We're going to measure drainage out. It's going to also be in units of cubic meters per day, and we're going to get 0.0050 cubic meters per day. So there's our precipitation, there's our drainage. So they're already in units of cubic meters per day, and the only thing left to do is to convert the change in mass of the monolith there, of the interior of the lysimeter, from kilograms to volume in cubic meters, and that will give us our change in storage. So this is the only sort of tricky part of these lysimeter problems. So our initial mass, our mass at the beginning of the experiment, we'll call that mass 1, was equal to 4,635.4 kilograms. Our mass at the end of the experiment, we'll call that M2, was 4,631.2 kilograms. So you can see that it's lost mass. Presumably that's the water that's evaporated, right? So the change in mass here, I'm just going to subtract one from the other, is going to equal minus 4.20 kilograms. So that is the kilograms of water that were lost to storage in our monolith. And all we need to do, really, the only, again, tricky part is to convert this change in mass to a change in volume. And to do that, we're going to use the very simple relation that you probably already know, right? You've probably written this down a few times, and that is that the density of fresh water, or the density of anything, is equal to mass divided by volume. Now, we are given mass, and we want to compute volume, but we know the density, right? We know that the density for fresh water is equal to about 1,000. This is a number you should probably know, 1,000 kilograms per meters cubed. So to use this equation, what we're going to simply do is rearrange it to solve for V. That's what I want to solve for. I want to know the volume of water equivalent to a mass of negative 4.20 kilograms. So I'm going to rearrange this to say that the volume is equal to the mass divided by the density. And here is my mass right over here, negative 4.20 kilograms. And here is my density, 1,000 kilograms per meter cubed. And when I plug these things in, I can write, I'll do it in yellow here to show that all my calculations are in yellow. So this is equal to negative 4.20 kilograms divided by 1,000 kilograms per meter cubed. And when I do that calculation, this turns out to be negative 0.0042 cubic meters, again, in one day, right? Everything happened in one day. So I have now the three things I need. Here's my precipitation. Here is my drainage. And here is this is my change in storage. I'll put that there. And remember, here is my equation here for ET, and I'm just going to plug in to this equation and calculate ET in the units of cubic meters per day. So here it is written out. So this is my precipitation. There's my drainage. And now remember, the equation says it's minus the change in storage, but the change in storage is negative. I just wanted to make that clear, so I put it in parentheses. And if I carry out that operation, I get that the ET in cubic meters per day will equal 0.0068. There we go. So there's the first part of my answer. I've got that done. Now I'm also asked to, let's just check here. Okay, we also have to calculate the flux. Remember the flux, this is an equation you used many times, right? The flux in length per time is equal to the volumetric flow rate, that's a meters cubed per day, for example, right? Divided by the area. And remember the area here, I'll just put it, just go slide up again here. We said that the area was 2.0 square meters. So let's just remember that, okay? So the area, I'm just going to write that to remind myself. The area of the top of the lysimeter is 2.00 meters squared. So to get my flux then, that's, okay, so my flux, ET, the flux in meters per day will equal the volumetric flow rate, 0.0068 meters cubed per day divided by 2.00 meters squared. And if I carry out that operation, I get 0.0034 meters per day. So let's put little circles around the answers here. So here's one answer. And this is the second answer I was asked to get here. And the third thing I was asked to do was to take this flux in meters per day and convert it to the more common international unit for evapotranspiration of millimeters per year, assuming that this same flux, the same flux we measured in one day prevails throughout the year. So I'm just going to have to make this into millimeters per year. So I'm going to take my flux here of my flux here of 0.0034 meters per day. First, I will convert that to millimeters per day by multiplying by 1,000, right? So that would be oops, I kind of moved my this, so I need to move it 1, 2, 3. So it's going to be equal to 3.4 millimeters per day. And then if I multiply that times 365 days per year, right, the days are going to cancel here, and I will end up with an ET of 1,241, which I'll just call 1,240 to three significant figures, millimeters per year, which is a perfectly reasonable rainfall, ET flux, there we go, for an area. There we go. So there are my three answers. The ET in meters cubed per day is 0.0068. In terms of a flux of meters per day, it's 0.0034. And in terms of the more common unit of millimeters per year, again, assuming that I'm getting that same flux every day of the year, I get 1,240 millimeters per year.